All right, we're going to take a look at limits at infinity. We've already done limits a long time ago, like in chapter 1. But all of our limits that we did before, we did like limit as x approached like 2 or something like that. And then we had, I don't know, x plus 1 over x minus 2. Right? We did things like this, where we had limit as x approaches 2. Before you could just usually plug in a 2, and then if you plug in a 2, you get a value. But on some values, it would actually go to 0 right here. And so you might have to come at it from the right side, come at it from the left side, come at it from both sides to find out what that limit might actually go to. Now, we did that in the past. That's, we'll have to come back to that a little bit later. But what we're going to do today is we're going to go, instead of limit as x approaches a specific number, we're going to go the limit as x approaches infinity, or negative infinity. But we're going to look at both. Okay, so let's go ahead and take a look at. Let's start with that. Yeah, let's start with that. Now we're just going to do a quick graphical approach to this, just to get an idea of what's going on, what we're actually looking for. But if we had just a regular old polynomial, pretend it was x squared plus 2 or something like that, it'd just be a parabola. The right and the left sides, they go on forever. They're unbound. They go up forever and on forever, and there's no restrictions on them at all. However, if we have fractions, if we have rational functions like such, we have different characteristics for what happens to the ends of the graphs. Okay, so ends of graphs for any kind of polynomial, they just go on forever, whichever way they end up going. Right side goes up, left side goes down. You guys probably remember a little bit of that. Anyways, if this rational function a little bit different for what we're doing on the very, very far right side and very, very far left side. That's what we're getting at with limit as x approaches infinity. Okay, so let's just look at a quick graph of this and see if we can figure out what's going on. So we can go ahead and just graph this real quick. And then let's see, we got 5x squared. We're going to divide that by x squared minus 1. Cool. It looks something like that. All right, so our graph looks ballpark something like that. I just threw it on there. Just going to try to get an idea of what's going on here. Now, I don't know if we've talked about it in this class. Now, have we talked about horizontal asymptotes in here? Yeah. Horizontal asymptotes, slant asymptotes, just a little bit. Okay. Well, what's happening is if we have rational functions, sometimes we can have horizontal asymptotes. Now, what a horizontal asymptote? An asymptote is a line that the graph will never cross. So, for example, there's probably an asymptote hiding right here, and there's probably an asymptote hiding right there. Little close. That's better. And then we actually have those are vertical asymptotes. Those are going straight up and down. Now we could have horizontal asymptote, and horizontal asymptote is that guy right there. We'll put it HA is. Yeah, horizontal asymptote. So if we know what the horizontal asymptote is, then we know what the limit is going to do on the far right side of the graph and the far left side of the graph. Now the far right side of the graph is as x approaches infinity. So our x value is right here. These are all of our x values. We're going x value as it goes to infinity. So we're looking at what happens when the graph goes that way in terms of x. Okay, so x is going to the far right here, and what number is this number getting closer and closer and closer to? Well, whatever that horizontal asymptote is, that's what number that the limit is going to be approaching. Okay. Likewise, if I did that same limit as x approached negative infinity would be going in that direction in terms of x. Okay. So as I look at that, I want to see what number this might be getting close to. I'm just going to plug in progressively bigger numbers. Okay. If I plugged in a real easy number, like second calculated value, plugged in like, I don't know, 5 or something like that, I get 5.2. Now I plug in a bigger number, like let's say 25. Ooh, go to. Sorry. Window's wrong. I might have to go through a table set to do this. Let's say I want to start table set at, top of table start at, let's say 1,000. And then change it by 1 every time, and then go to my table. I could change it by bigger. Ooh, look at that. It's going to 5. Okay, and as I go up here, it's still going to 5. If I go to my table set, let's say I wanted to start at, I don't know, I could start at 5, and then I can change my table set by 100 if I want. You can do it any way that you'd like. Go back to your table, you get, let's see, 5 point, well, it's getting close to 5 out here. 501, 506, 504. And notice it's getting closer and closer and closer to 5. Because it is 5. It is 5. The horizontal asymptote for this was 5. 1, 2, 3, 4, 5. So the answer for this limit right here equals 5.
Nice.
It doesn't get that much harder than that. The concept is that right there. The concept is that. So, we're okay so far?
Yeah.
All right. Now there's 3 different situations that can happen when you're talking about rational functions. There's only 3. Okay. The first situation is this. Notice the exponents that are happening right here. The exponents is x to the second power and x to the second power at the bottom. So as far as the numerator is concerned, the degree of that polynomial is x to the second, right? It's 2. The degree of the denominator is also 2. Since those degrees match, since they're the same, they both have the highest degree. When I plug in a really, really big number right there, those end up going, well, they end up going at the same rate. So if those two go at the same rate, you're left with 5. 5 is basically the leftover. It's the factor for that number in the front. So that number just happened to turn into to be 5. Happened to be. Okay. Now I do want to show you one little extra thing. Let's do this. This is where all this kind of stems from. When the limit is x approaches infinity, this works for negative infinity. This would be your first big theorem if you want to say it. Let's say I have 1 over x. Okay, so that's a real basic function, 1 over x, nothing super hard about that. But if I plug in, let's say I plug in a 1 right there. What do you get if you plug in a 1? 1. What do you get if you plug in, I don't know, 100? 1 over 100, that's really, really small. What about 1 over a million?
0.
Really, 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 really small. Chances of winning the lottery. 1 over, like 6.2, what is it, 6.4 trillion chances of winning the lottery? 1 in 6.4 trillion. No, it's billion. It's just billion. 6.4 billion. 1 in 6.4 billion right now. Anyways, the bigger number I plug in here, right, it gets to be really, really, really small. So what's that limit turn into?
0.
0. Okay, that's getting closer and closer and closer to 0. Okay, everything is really based off of this theorem right here. This is a theorem right here. And technically, it doesn't matter if I go x to whatever power. So technically, I think the book uses r. I think you can use whatever letter you want. But if I have some number, the number happens to be 1, what if I change that number to a 10? Is that going to matter? 10 over 5 billion? No, it's not going to matter, right? It's still going to be really close to 0. Okay, so the book might write that as like a letter C. Some constant, some number, a million, doesn't matter. If I plug in like a trillion or 8 bajillion trillion in there, that's just gonna dwarf the million. So that constant doesn't matter. Okay. So this is gonna get closer and closer to 0. This also works if I plug in negative infinity. And negative infinity would just make this get closer and closer to negative 0. Well, you can't really have a negative 0, right? So it's still gonna get closer and closer to 0. Now, ultimately, what we're trying to do is use this theorem on this guy right here. So mathematically, algebraically, this is what's happening behind the scenes. Okay, even though it's real easy to see, the answer would be just 5. This is what you would want to do with. Oh, one more tiny theorem I do need to show you. This is real quick. But if I take the limit, and this works for anything, right? I might have already shown you this, but if I have f of x and then plus g of x, if I'm taking the limit of that guy right there, you can just take the limit of each individual, right? You really don't have to.
Oh, okay. I'm going to write it down.
But it's good to have it. Anyway, so you take the limit of each one of those and just add those together. So you can separate those. You can isolate each individual one. That also works for multiply. They got it in the book. I don't know what page it's on. It's in that section. So if you want to get like the official, mine might not be perfect as far as like what I don't really like right now on this thing. Ooh, it's pretty close to what I had, actually. That one right there. A little out of focus. Sorry. There's also a multiplication one. Multiply, you can take the limit of each and multiply it. It doesn't really matter because you're just plugging in a number, so it doesn't really matter at all. Anyways, what we want to do is we want to try to figure out the algebra behind this to see where that 5 came from. Okay, because I think you guys see that the 5's there, but this is the algebra behind it. So let's go ahead and do it. Let's do limit as x approaches infinity, and we're going to do 5x squared divided by x squared minus 1. What I want to do is I want to get it into this format right here. I want to have some number divided by some power of x to some power. So what I would do is I would take the highest power that's in there. Highest power is x to the second power, right? Highest power x to the second on the denominator right there. I'm going to divide everything by x squared. So I'm going to divide everything by by x squared. Okay, so divide each term by x squared.
Well, where'd you
Now, a lot of this is overkill, the one right here.
X squared.
I divided everything by the highest exponent, x to the second. So I just divided each term by x squared. You'll see why in a second.
Alright, let's watch.
Okay. Now what happens if I divide by x squared here? Cancel. Cancel to 1. And then that doesn't cancel, right? But we're left with a 5 on the top, divided by 1 minus 1 over x to the second. Okay, now just on the inside of this guy right here, I'm taking the limit as x approaches infinity. What's 1 over x squared going to turn into? 0. This is going to turn into 0 if I go 1 over x squared as x goes to infinity. So I'm left with the 5 on the top, 1 minus 0 on the bottom, so 5 over 1, so you get 5.
That was really
Okay,
weird.
can you go over that big part right there? 5 squared.
This part right here,
Yeah,
I divided this by x squared, this by x squared, and this by x squared.
got it.
So 5x squared divided by x squared is that. X squared divided by x squared is that. And then 1 divided by x squared is that. We will do another.
Wait,
I'm
I'm
waiting.
having difficulty.
So the 1 over x squared.
Limits and derivatives.
There is no difference.
They're the same?
You're perfect. You're out of the money.
Okay.
Yeah. Because what a derivative is limit as x approaches 0 of that. Oh, actually, h approaches 0.
This is,
Oh, my recycle box. All right, now, like I was saying, there's 3 different situations for how this is going to work. Let me draw a couple up here. Let's do 2x squared plus 5, and then divided by 3x squared plus 1. I want to do the limit as x approaches infinity. Now, as I look at this, as I do this, first thing I would recognize is they're both x to the second powers. So you guys might intuitively know the answer to that. Maybe. Any guesses?
2/3.
That'd be wrong, but. All right, now there are 3 different ways, three different ways that this could actually work. So if you want to remember the 3 different ways, that's fine. Or if you want to just remember the way I'm showing you right now, that's also fine. But x to the second is my highest exponent. I would divide each term by x to the second. So it would be 2x squared over x squared plus 5 over x squared, and then divided by 3x squared over x squared, and then plus 1 over x squared. So I divide everything by x squared.
Oh my god.
Okay, x squared cancels, so you're left with 2 plus 5 over x squared, divided by 3 plus 1 over x squared. That's what you're left over with. Okay, well we have a constant divided by x squared. So what's this going to go to as x goes to infinity? 0, right? So this is going to turn into 0. What's this going to turn into? 0. So you're left with 2 divided by 3. Cool.
So when it's in that form where the
You're going to say something so perfect here, I want everybody to hear it, so listen up. He's going to say it so good.
whenever the variable is on the bottom, it's 0. That probably wasn't.
Oh, that's not what I thought you were going to say, but okay.
Whenever it's in that like limit.
I thought you were going to nail it. I thought you were going to nail just the original right here. When you have something like this,
you just negate the constant.
When there's a.
notice these powers are the same. They're both x to the second powers.
They're the same.
It's just going to be the leading coefficient. That's exactly right. Okay? So if they're the same exponent, x to the second, it's just the leading coefficient. It's just the numbers that are in the front, 2 divided by 3. That's it. So there's a lot of work here for, well, not a lot of work, but there's a little bit of work here for just seeing that it's 2 over 3. Okay?
Give it kind of.
It's an understanding. It might take a couple of these to figure out, but anyways, that's the idea of it. Now that's if they match. What happens if they don't match? Right? That's the real problem.
Then you have to do this part we've been doing, right? Doesn't matter.
No.
No, okay.
Almost the exact same problem. I just took the little 2 off. Limit's still approaching infinity, yeah. Actually, we'll make it real hard on this. X will approach negative infinity.
Oh.
It doesn't change anything except for on radicals, which we'll have to talk about in a second. Now on this one, we have an x on the top and we have an x squared on the bottom. Now our ultimate goal is to get a number divided by whatever the letter is going to be, okay? Well, on this particular one, x squared is my highest exponent. I'm going to divide everything by an x squared and see what I get. Okay, so divide everything by x squared. 2x over x squared plus 5 over x squared divided by 3x squared over x squared and then plus 1 over x squared.
This is really easy, isn't it?
Not yet. I got to show you the hard ones still. We haven't done the hard ones.
Just checking. We should have not taken it.
Actually, I probably could just write down your homework and then if people want to start it.
I go,
0. 0 over 3. Oh, 0. Zero there. Right, I think. So if it's smaller on top, it's always 0.
oh.
It has to be, right?
Yeah.
No matter what? Cool. Say that out loud because that was perfect. Kind of jumped the gun there a little bit, but that's okay.
If it's smaller on the bottom.
Yeah, if the highest degree is smaller on the bottom, then it's undefined. Okay, and the reason is because this is really, the top here is 0 plus 0, so it's 0. Divided by 3 plus 0, so it's 3, so that's why it turns into a 0. Now, if the exponents were flipped over, right, this would just be flipped over then. So it would be 3 divided by 0, and you can't divide by 0, that's undefined. Okay, so then you wouldn't have an asymptote there. And I don't know if you remember slant asymptotes, but you couldn't have a horizontal asymptote and a slant asymptote at the same time, because the slant asymptote had to be bigger on top by 1, exactly. So like, for example, if this were to the third power, like that, exact same problem, but that's now to the third power. This would be an undefined limit. This limit wouldn't go to a, this wouldn't, unless it had a slant asymptote, so the graph would actually look something like this. And it was one of those weird ones where it, I don't know if you remember those. It was like that. Anyways. Where the slant asymptote. Now, the thing is, it was bigger on the top, and so since it's bigger on the top, that would go to undefined. Now, if you don't remember the little tricks, all right, if they're the same coefficients, if it's bigger on top, it's undefined. If it's bigger on the bottom, then it's 0. Those are just little tricks to remember that. You could always just remember, all right, just divide everything by whatever's there, and then I know this part is 0. 1 over anything is going to be 0. 1 over any x value. So. Anyways, the only tricky ones, that's if they're in nice little rational formats like this. The only tricky ones are if you have a radical or a square root going on. Those tend to be a little bit different. The concept behind all of it is still the same, but how you would do this is a little bit tougher. But I do want to show you just 1 or 2 real quick square roots, and then I'll cut you loose. Okay. Cube roots you don't have to really worry about too much. So the way I'm going to show you, it's not really going to matter. But if it's an even power root, you have to be cautious. You have to be careful. We're actually going to do 2 limits on this problem, but 3x minus 2 and then divided by. All right, now mathematically this would be a little bit tougher one to do. I would first want to divide by, well, the numerator right there is x. So I'm going to divide that by x and just see what happens on the rest of it. Okay. Now if I divide this by x, it gets a little tricky because you got 3x over x minus 2 over x. Not too tricky there. But then divided by this guy. If I divide that by x, hold on, time out. 2x squared plus 1. If I divide that by x, that really doesn't get me anywhere, right? Well, if I want to put that x inside the square root sign, what would I have to do to that x right there? I'd have to square it, right? X really equals the square root of x squared, right? So I can just replace, instead of putting an x in for that one with the square root, I'd really want to put in the square root of x squared. So the square root of x squared, same thing, same idea, it's just still x. I'm still dividing by x right there. And then see what's left over. So we get 3 minus, let's see, 2 over x. And then divided by, now this is all inside of the square root, right? So I'm going to do a little bit of work inside the square root. This is one big square root now, 2x squared plus 1, and then I'm going to divide this by x squared and divide this by x squared. Oh dear. Okay, so I divided both by x squared on the inside of that square root. They both have a square root, so you can put the square root over the whole fraction. All right, and then so we have the square root on the bottom. We've got 2 looks like. X squared cancel. And then plus 1 over x squared, so plus 1 over x squared. Cool. Now, as x gets really big, this goes to 0. So we get a 3 on the top. And on the bottom here, on the bottom, x gets really big. Right? So x gets really big, and so that part goes to 0. So I'm left with the square root of 2. Cool. So you get 3 over the square root of 2. That would be that horizontal asymptote. I'm going to show you a shortcut in a second here. But
So it's the thing.
show you a little bit of a shortcut. Tiny, tiny, tiny. So ready for it? All right. This is really,
One bigger.
this is 2x squared plus 1 to what power? To the 1/2, right? Now, if you were to FOIL stuff out, which is kind of hard to do with the 1/2, but if you were to FOIL stuff out, right, the leading coefficient would be 2x squared raised to the 1/2 power, right? That would be the highest exponent that's ever going to be in there, right? Well, what's the square root of 2x squared? It'd be the square root of, I'll just write it 2x squared, I guess. Square root of 2x squared, which is the square root of 2 times x, right? Well, the exponent here is really a 1, and so now these exponents match. X in the first, x in the first. So it's just the leading coefficient, which is 3 divided by square root of 2. Do you see that?
Just divided by the root.
You take the root of it, yeah. Yeah. Don't divide it by the root, but take the root of it. Yeah. Different things. It is. It is a little bit different when we approach negative infinity. With the square root sign, we plugged in x equals the square root of x squared. That's all fine. Nothing wrong with that, right? But the problem is if I had x squared and I were solving for something, right, and I took the square root, right, I take the square root, I got to do plus or minus, right? Well, if I'm talking about x getting really, really, really big positively, my x value is going really far positive, it's no big deal to plug in a positive value for this 3 over square root of 2, or plug in a positive value here. Now, if I'm approaching the limit as x approaches negative infinity, on a square root one, that's going to change things a little bit. On a square root one, we actually have to plug in a negative square root of x squared. Because technically, if I'm solving for stuff, it's plus or minus. I would use the positive when I use positive infinity, and negative when I use the negative infinity. Okay? Now, you can still apply that same rule. You can still think, all right, it's really 3 over the square root of 2. That's my leading exponent. But then this denominator, you would want to switch the sign on that. Okay? So the limit for this guy, if it were approaching negative infinity, is going to be negative 3 over square root.
Do you have to rock?
I don't really care, to be honest with you. You could if you want. I'm not going to mark you wrong if you do it. But so, anyways, I want to show you one more quick square root run, and then we're good with the square root stuff. Okay? What do you want me to write down? I'll write down the assignment because I know some people are dying right now. Ooh, I was going to do. Oh, we didn't even do the squeeze theorem either. Squeeze theorem. You won't be able to do 31 and 33 until you see what I'm going to show you right now.
At this time, would you please release seniors to report to the theater? Seniors to please report to the theater. Thank you.
Oh.
Hey, Bill, can you keep the assignment back up there real quick?
Less homework that I have to do.
Where we going?
Well, if people want to do the makeup quiz, you can start right now if you'd like, and just go through pause. That'd still give you 40 minutes. Should be enough. 40 minutes. All right. And then I'll show you this last little problem, and then we'll be good.
Are you gonna show everything?
What? Yeah, I just want to let people start on their quiz, and then they can go through pause. Okay, last one real quick here. Got to show you one little extra trick. Free world. All right, and the problem is this one doesn't look like any rational function that we've done so far at all. So there's one little extra trick that I do want to show you on this is really over 1. And so what we want to do a lot of times when you have a square root sign, you can rationalize the denominator by multiplying this guy by its conjugate. And the conjugate for this, I'm sure you guys remember this, but the conjugate is the exact same thing. You just switch that sign on the inside right there. So we're going to multiply the top and bottom by 3x minus the square root of 9x squared minus x. Okay, so we're going conjugate. So we got, now, the nice part about conjugates is you just do Florida, just do first and last term. So these two and then those two. Inside term, outside terms cancel. Basically, it makes the square root go away in the numerator. That's a good thing on this. So we get 3x and 3x, which is 9x squared. I hope. And then minus the inside of the square root. So it's going to be 9x squared minus x. Okay, so we're subtracting everything that's on the inside of that square root. This is the numerator. I'm just going to do the numerator real quick. And 9x squared minus x squared goes away. And then minus negative x, so you get a positive x for your numerator right there. Now your denominator, you get 3x minus the square root of 9x squared minus x. And limit as x approaches negative infinity. Now you do have to be a little bit cautious when you're doing the square roots as you go to negative infinity with square roots because yeah, you got to think of it as a negative number when you're done. So, all right. Anyways, the highest exponents on this, I might show you just the shortcut on this. I think that would be okay. And so you could divide everything by an x. So you can divide this by an x, and then this by an x, which is really the square root of x squared with a negative sign in front of it. Okay. But anyways, notice what the highest exponents are going to be. Okay. The highest exponent for this one is x to the first. Highest exponent for this one is x to the first. But what's going to be the highest exponent for this guy? Also x to the first, right? It's x squared and then the square root of that. So those square and square basically cancel. Okay? So what you're left with here is the coefficient for this one. Coefficient for this one is a 1 on the top. On the bottom, the coefficient for this one is a 3. And technically, this was also a x to the first term right here. So this would be square root of 9, which turns into 3. So it's a subtracting 3. Now, we have to do negative because of that square root sign. So it would be a negative 3. So then we just get 1 over 6.
What about the negative x scale and a half?
You don't care about that because it's a lesser power, right? So when you divide, it would end up being like 1 over x to some power. So it would just go to 0 anyways. So you don't really need that. But anyways, it's a little tougher because there's more than one leading coefficient. There's more than one of the highest degree. We have an x to the second, and then that's, to the 1/2 power. So really that's an x to the first. I might show that the long way, but that's the short way to do it. Divide each of those terms by x. So this would be x over x divided by 3x over x minus the square root of 9x squared minus x. And then I can divide that by the negative square root of x squared.
Why is it negative?
Because x is approaching negative infinity right there. Since x is approaching negative infinity, I have to use a negative x for that one right there. Now, if you did that on the other ones, since you're approaching negative x, if you did it on the other ones, I don't think it would change the problem. I think you can do it on all of them. But on the squares, I know you have to do it that way on the squares. So, anyways, the fact that you're subtracting a negative right there, those two are just going to become positive, like so. And then divide each one of those terms by x squared on the inside. Top here is 1. Bottom is 3 plus the inside of this would be the square root of, looks like 9x squared over x squared, so that's 9. And then negative x over x squared, so that's a negative 1 over x, which is going to go to 0. So you get 1 over 3 plus the square root of 9 is 3, which gets you right back to there. Sure. These are tough to make up. Should we do positive infinity or negative infinity? Or? We can do both. Yeah, if you can do negative, you can do positive. So, let's do Where did that last one go? Oh, it's back here. I'm gonna cheat though. Ooh, do I want to cheat? How hard do I want to cheat? Cheating is bad.
Will they always be good squares?
Well, no, because the last one was square root of 2. So, not necessarily. Of course. Of course. I think I was going to do the evens Friday, so. Like, if you want to just do it straight through, that's fine.
Okay.
Actually, I might add a little bit Friday this week. Friday's only half an hour of class.
And
Up the fun and the glow stick dancing.
huh?
Oh. The assembly on
Yeah.
Friday, right? Isn't that always the glow stick assembly?
Yeah.
It's like the spring recognition. Oh, no, it's not spring recognition. It's end of year assembly. Did we do a spring recognition? Oh, I think we did. Spring sports. A spring sports assembly.
I think so, yeah.
I see what it is. I don't want to eat. No. Did you put that on the floor? No. Wait, is it? No? Okay. Uh-oh. Yeah, it's negative. It should be negative.
Uh-oh. Uh-oh.
Or is it undefined?
It's undefined.
Yeah, because it'd be or and then it'd be negative.
I meant positive infinity.
Gosh.
My bad.
Scratch that.
Scratch that.
So it'd be negative 180.
The negative 1/8.
But if it was negative,
It'd be undefined. It wouldn't have. It just wouldn't have a limit there.
it would be minus.
Because it'd be 4 minus 4, and so it would be 0 on the bottom. Actually, probably could have left it as negative infinity and just got it undefined. But notice it's undefined on one side and it is on the other side though.